Welcome back. So we have seen in our case study that the client has a reference to the module dict. And we noticed that a more configurable client, and the more reusable one, would let us choose the dictionary implementation in a second time, externally, when the module is already compiled. That will be exactly the purpose of a module functor. Our functorized client will have a reference to a module which implements the dictionary interface. So let us come back to the example of the case study. We have this module type for dictionary that isn't changed. And now we want to be able to reuse the client afterwards on different implementation of this dictionary. So we introduce a functor, which means that in the code we add an argument, but this argument takes not a value but a module dict here, and we provide the signature for this module. The rest of the code is unchanged, but now we have not a module, but a functor, that is a parameterized module. If we have two different implementations for the dictionary, like this, on list, and like that on binary search trees, now I can define not only one client, but two clients. A first client that is implemented using the dictionary represented as list, and another client whose dictionaries are implemented using binary search trees. A functor is a function from modules to modules. So a functor is a module waiting for another module. The syntax to define a functor mimics the definition of a function. You start with standard syntax for module definition, and you just add after the identifier as an argument the module that you are expecting. This module must be constrained by some signature. In that case, OCaml is unable to infer the type of the module of a functor argument. As any function, a functor can be applied. So to apply a functor to a module, you just use the name of your functor, and between parentheses, the modules that you want to provide to the functor. In fact, this module can be a module identifier, but also directly an implementation using struct and end, or even another functor application, so that you can chain the application of functor if you want. The language of signatures is extended to be able to handle functor. We have just a new keyword, functor, with the type of the argument and the name of the argument, an arrow, and a signature. The type that are in the argument can be mentioned inside the definition of the signature. If you go through the documentation of the standard library of OCaml, you will discover two very interesting modules and very useful ones, set and map. In fact, these two modules define functors that are waiting for another module satisfying the following signature. So this signature is named ordered type because it contains a type t, which is equipped with a function that compares two values of type t and produce 0 if these two values are equal, and -1 if the first one is greater than the second one, and 1 otherwise. Then, if you are able to construct such a module, and you apply the functor set.make on it, then you will get a very large number of functions that manipulate sets whose elements have type e.t. Similarly, if you apply map.make on this module, you will get a large set of functions manipulating maps whose keys are of type e.t. So remember another remark that we have done about the case study in the last sequence. We have said that it was a pity that the exception not found cannot be adjusted in a way that it carries the key that has not been found. It would be a more informative exception. But it was not possible because the type parameter quote key should then be shared between the type of the dictionaries and the type of the exception, but the type of exception in OCaml cannot be polymorphic. In fact, such a type parameterization can be done using a functor. So, let us come back to our example of the case study. We had a signature that was a bit different from the one that we have here. So previously we had a parameterized type with two parameters, but we said that we want to share the type parameter key between several definitions. So we have split this type in two. And now it is a component of the signature of the module. It's simply a type key that should be given inside the type of the module. So now this type key can be used not only in the definition of function like this, but also in the definition of exception. So now not found can carry the key. How can we now implement a module that fulfills this signature? Well, we have to provide a way to give this type key. So we will give it through a module argument. So dict is now a functor. It is a function from module to module. So it takes a module key whose signature is a type T, which is a type for keys, and also a comparison function working on keys. We can use this module inside the implementation of the functor body. So type key can be equal to the module key which was given as an argument dot t. So the type t in the provided module. That's nice. After that, the code is essentially the same as before, except that during the lookup, you can use now the comparison function that is found in the module argument to compare the keys when you are looking for some keys. Okay, so let's see if this is working. So first evaluate the signature, after that the functor, and we can notice that the inferred signature indeed introduce a functor with a description of the signature of its input module. So now we can apply this functor on a module that defines a type for key which is equal to string, and let's say that to compare two keys we will first lowercase them, so that if there is some cases that are different between two keys that means the same, they will be made equal by this comparison function. So this one is accepted. We now have a dictionary, and let's try to use it in a client. So our client is now a functor that is waiting for a module implementing the signature for dictionary. So let's try to evaluate this. Oh, we have a typing error. It says, Luke is a string, but you must provide a dict.key. Oh yes, dict.key is an abstract type, so there is no reason that it is equal to string. So what we have to do is to express the fact that here the type key must be equal to string. Okay? Because after that, with this extra information, the program that was rejected will be accepted. So what I've written here is what is called a typing constraint that is put on a signature. It's a way to give more information to the body of the functor. So let's see if this is accepted. Oh yes, it is. Nice. Can I continue? Yes. I can try to now instantiate some archive using this functor and implementing the dictionary using the first implementation of the dictionary. Is it accepted? Oh no! Why? Ah, yes, I see why. Dict1 is a module that also has the type for key that is abstract. So I have to, again, express more information about the relation between the type of the key of the output module and the type of the key of the input module. And again, I can use a typing constraint to do so. So I will write a new functor for dict that says that the output module will fulfill the typing constraint that the type key that is inside this module is equal to the type key that is provided in the input module argument, the module key. And now, even if these two types are abstract, they are made equal in the output of the functor. If I try now to apply the force archive functor to dict1, dict1 is now has to be redefined too. I do it right now. See? Okay. So if I now apply my functor, it's accepted. And moreover, I can see that now my exception is informative, saying that R2D2 is not a Jedi. What we have seen with this example is first a very nice way to to implement a type parameterization between several components, an exception definition and values and so on. But also, we have seen that sometimes type abstraction must be relaxed a little bit a posteriori, afterwards. And that's exactly the role of a type constraint. It expresses the fact that some type in a signature, which is abstract, verifies, satisfies some constraints, some equality with other type. So when you have a type constraint in on a signature, it restricts the usage and the definitions of the functor you are defining. But in exchange, the functor client will get more guarantees about abstract types. The fact that two types, for instance, share the same definition, even if you don't know exactly what this definition is. The syntax to put a type constraint on a signature is just a signature and then a sequence of type equality that are introduced using the keyword with and separated using the keyword and.